Right. So let's talk about the third law of thermodynamics now. The third law of thermodynamics says that the entropy of perfect crystalline substances approaches the same value as temperature approaches of absolute zero. As a matter of convenience, we take that value to be zero. Okay. So why is it convenient to take that value as zero, to be at absolute zero to be zero? Because that puts it in line with our notion of what? At absolute zero, how many ways can you distribute thermal energy among the molecules? One way, and natural log of 1 is 0. Okay, so that's a good way to justify taking it as 0. But the third law of thermodynamics simply says it approaches the same value as temperature approaches absolute 0. So let's look at this reaction then. Based on the third law of thermodynamics, what is the delta S for this reaction at 0 Kelvin, at absolute 0? You have methane solid plus O2 solid gives you CO2 solid plus water solid. Okay. I didn't balance this. To balance this, I need 2 here. 2H2O. Okay. What's the delta S for this reaction at 0 Kelvin? 0. Okay. Assuming all of these are perfect crystalline substances at 0 Kelvin. Okay. Now, we just talked about the statistical interpretation of entropy. It's a measure of the number of ways that a system can exist, right? And primarily, we said that's in most cases, it's just going to be the number of ways that your thermal energy can be distributed. So we say as temperature approaches absolute 0, number of ways approaches 1, and the entropy approaches 0. But entropy will not be approaching 0 as the temperature approaches absolute 0 if the solid is not perfectly crystalline. How can a solid not be perfectly crystalline? Well, if there's more than one way that the molecules can settle into the solid. So for example, in an HCl molecule, there's 2 ways your HCl can be oriented in a crystal. It can be either, you can have H on this end and Cl on that end, or you can have Cl on this end and H on that end. Okay? So there's 2 ways. So the entropy per mole for solid HCl, okay, would be approaching K times natural log of 2 raised to the power n sub A. If you have a mole of HCl molecules, okay, each one of those molecules can be oriented one of 2 ways as they settle into your solid. So the total number of ways it can happen, okay, number of ways that they can settle into your solid would be 2 raised to the power n sub A, where n sub A is Avogadro number. So if I move this thing over to the left, Avogadro's number is times Boltzmann's constant, that's R. So RlN2 would be the value that you will be approaching at absolute 0. Okay? Now, if you can get your HCl molecules to all settle one way, one specific way, you'll have a perfect crystalline sample of HCl, then its entropy is going to approach 0 at 0 Kelvin. Okay? So this RlN2 right here is what you would call the residual or the configurational entropy of HCl. So you can make corrections for those, and so that you can get what we call standard entropy. Standard entropy is the absolute entropy of any substance, refers to the entropy change where you start off. Imagine you have your substance as a perfect crystal at 0 Kelvin at 1 bar pressure. Standard here means 1 bar pressure, okay? Imagine you have a perfect crystal at 0 Kelvin, absolute 0, 1 bar pressure, okay? You heat that crystal at constant pressure of 1 bar and take it all the way to 298 Kelvin, okay? And then imagine that substance, if it's a gas, if it happens to be a gas at that temperature, imagine that it's behaving ideally. Okay, the delta S for that process would be called the absolute entropy of your substance, because S at 298 K minus S at 0 Kelvin would be the delta S for that. But what's S at 0 Kelvin? we're taking that as 0. So the delta S for that process would just be what you would call the standard entropy or the absolute entropy of that substance at 298 Kelvin. Okay. So how do we measure standard entropies? You measure heat capacity versus temperature. Okay. And what we're going to be doing in the lab is we'll be using a differential scan. We're not going to always, obviously, we're not going to be able to go all the way down to very low temperatures. But one instrument you can use to measure heat capacity is a DSC, differential scanning calorimeter. So we'll be doing an experiment in the lab to measure heat capacities. Okay. So what you do is, if you can get your heat capacity is measured to as low a temperature as you can, okay? And then what you do is once you get to the lowest possible value, you can extrapolate to absolute zero using the Debye T-cube law. And this Debye's law says that the heat capacity as you approach absolute zero is directly proportional to the cube of the absolute temperature. So AT cubed, where the constant A depends on what the substance is. Okay? So what you need to do then is just, you have the formulas for delta S for heating, you have the delta S for phase transitions. All you have to do then is you integrate Cp over T from 0 to 298 Kelvin. Okay? So your S at your total delta S would be integral of Cp dt over T from 0 to 298 Kelvin. But along the way, as you're heating your substance from 0 Kelvin to 298 Kelvin, there could be phase transitions. So delta S for all of those phase transitions will just be delta H divided by the temperature at which those transitions occur. Okay? So let's take a look at an example here. Here's how the calculation of the standard entropy of nitrogen is done, as illustrated in a couple of textbooks. The one by Atkins is 8th edition, same numbers in 9th edition. This is your textbook right here. I think this, let's see. This is the one from Atkins, okay? And this is the one from Macquarie and Simon. That's another textbook. And you'll notice there's a discrepancy in their numbers. Okay, so which one would you trust? Okay, look, from 0 to 10 Kelvin, okay, Macquarie and Simon is extrapolated delta S to be 2.05 joules per Kelvin per mole. Atkins gives you a number of 1.92, okay? And then what happens from 10 Kelvin to 35.61 Kelvin? Where would this, okay, first of all, where would this number come from? That's going to be, okay, this number would come from delta S from 0 to 10 Kelvin. What would be the formula for delta S at constant pressure heating? It's just Cp dt over T, okay? So let me write that down here. Delta S from 0 to 10 Kelvin would be integral of Cp dt over T from 0 to 10. And the Debye T-cube law says that Cp right here is AT cubed, okay, dt over T from 0 to 10, okay. And what is that, AT cubed? Integral of AT cubed dt over T. What would that be? I can pull out the A. What's integral of, what's T cubed over T? T squared. What is integral of T squared dt? T cubed over 3, right? Evaluated from 0 to 10 Kelvin, right? So that's just, but what is AT cubed? Cp is just AT cubed, right? So that's just Cp over 3. 1/3 Cp. Okay? So this is Cp at 10 Kelvin minus Cp at 0 Kelvin. What is Cp at 0 Kelvin? is going to be 0, right? So when you plug in T equals 0, Cp is 0. So it's just a Cp at 10 Kelvin. So 1/3, right? Divided by 3. So whatever the Cp is at 10 Kelvin, you just divide it by 3. That gives you your value for delta S going from 0 to 10 Kelvin. Okay? So looks like Atkins and Macquarie were using different values because Macquarie and Simon has 2.05, Atkins is 1.92. Now, what's delta S going from 10K to 35.61 Kelvin? What would that be? Integral from Cp dt over T from 10 Kelvin up to, how much was it? 35.61 Kelvin. Okay, and you get a number there. Okay, experimental values are available for that one. Okay, and so the number, you can see the numbers are pretty close, 25.79, and Macquarie and Simon gives 25.25. Okay. Now, why did we stop at 35.61 Kelvin here? Because at 35.61 Kelvin, there's going to be a phase transition for nitrogen. Okay? At 35.61, nitrogen undergoes a transition from one solid form to another solid form, from one crystalline form to another crystalline form. And so where did the 6.43 come from? That's delta H for the transition divided by, so say then that delta S at 35.61 Kelvin is the delta H for the transition at that temperature divided by 35.61 Kelvin. Okay? So that's the heat of the enthalpy change for the phase transition occurring at 35.61 Kelvin, where nitrogen undergoes a phase transition from one solid form to another, one crystalline form to another. And then what happens after that? You integrate this time from 35.61 to 63.14. Okay? So in the next step, you integrate from 35.61 Kelvin to 63.14 Kelvin. What's the formula for delta S? Simple, heating at constant pressure. Cp dt over T. Okay? And these are the numbers. And notice there's a slight difference here in the temperature that they used. Macquarie, I think I've got these two switched. Yeah, this is not Atkins. This is Macquarie and Simon on the left. And this is Atkins on the right. Okay, so this one ends at 63.15. The other one ends at 63.14 Kelvin. What happens at why did it stop at 63.15 or 63.14? What happens at that temperature now? Melting occurs. So this is delta S of fusion, entropy change for melting at 63.14 or 63.15, depending on whose table you're looking at. Okay, so that's the delta S of fusion. After that, what happens? So at that point, what do you see? Delta S fusion. So the delta S according to this at 63.15 Kelvin is delta H fusion at that temperature divided by 63.15 Kelvin. So your nitrogen solid melts at 63.15 Kelvin at 298 Kelvin. According to Macquarie and Simon, it melts at 63.14 according to Atkins. what happens after that? Once something's melted, what do you do with it? You heat it up to its boiling point, right? So from 63.15 Kelvin to 77.36 Kelvin, you raise the temperature of your liquid to its boiling point. And so what's the boiling point of nitrogen then, according to this table? 77 Kelvin is where nitrogen boils. So what's the temperature of liquid nitrogen? We got liquid nitrogen. That's where your nitrogen gas liquefies. So that's at the boiling point, right? So 77 Kelvin is the temperature of liquid nitrogen. And then what's the next calculated number here? That's delta H of vaporization. And so what's the next one after that? That's a delta S in heating your gas from 77 Kelvin to 298 Kelvin. Okay? And then you have to, since it's a gas at 298 Kelvin, you have to do a calculation, a correction, which is going to be correction for non-ideal behavior. All right? Because the numbers that you find tabulated, okay, as a standard entropy or absolute entropy at 298 Kelvin are numbers that are based on the assumption that the gas is behaving ideally. And you'll notice these two numbers don't agree either. 0.02 for McCurry and Simon. For your textbook, it's 0.92. Okay, so which one is right? The numbers are very close at the end, though. 191.6 versus 192.06. Look at the NIST web book, you'll find the absolute entropy or the standard entropy of nitrogen is 191.61. And let's look it up. You go to webbook.nist.gov. Go to chemistry web book, you search for nitrogen, N2, okay? Gas phase, condensed phase, phase change data. And let's see, here it is. Absolute entropy, 1 bar, is 191.609, 191.61, as recently reviewed as of 1998. Data reviewed March 1977. So, which author gives you a closer number? Looks like McQuarrie and Simon's number is correct, huh? So anyway, that's how you calculate the absolute entropy. What time is it? We still have some time. 27. We got plenty of time. All right. Now the Debye extrapolation. If for nitrogen, let's take the value of the entropy at 10 Kelvin to be 2.05 joules per Kelvin per mole. What's your A in the expression Cp equals 8T cubed? Then Cp at 10K we said was just 1/3. It's just equal to what? What did we just show? Delta S would be 1/3 of Cp at 10 Kelvin, right? So what would this delta S be? 2.05 joules per Kelvin, right? Per mole. And what is our Cp then? Cp naught at 10 Kelvin will just be 3 times the absolute entropy at 10 Kelvin. So 3 times 2.05 joules per Kelvin per mole. Okay. So 3 times 2.05, that would be 6.15. Okay. Non-ideal correction. And this is why I would say I would trust Macquarie and Simon's number, because if you calculate the non-ideality correction, you'll find it to be 0.019. And if you go back to the two tables, the number you get is 0.02 from Macquarie and Simon. Okay.
How did Atkins get such a different
I don't know.
correction for
At first, I was thinking it might have been a carryover from a switch between 1 atmosphere to 1 bar in terms of the standard pressure. But if you go from, let's say, which one's higher, 1 atmosphere or 1 bar? 1 atmosphere is a higher pressure, right? So if you have a higher pressure, would you expect a higher boiling point? You would, right? And according to this, Atkins' number, his boiling point is 77.32. But Macquarie's boiling point is even higher, 77.36. So I thought that might be the reason why there's a discrepancy, but I don't know why the discrepancy is occurring. Okay? But based on the literature values I've seen, looks like Macquarie's value is correct. All right. So delta S for nitrogen. Okay. To do the non-ideal, is it time to go? Okay. We'll discuss the correction for non-ideality next time. All right.